everything from this point on, everything that's projected on the board and that I say picked up by the microphone in my computer is recorded in sync. But just like Nola's experience, it takes about an hour or two for it to load to YouTube, and then it takes me a while to go in there and get it moved to the playlist. But today, since I don't have any classes after this one until I have to leave at 4:30 to go to the Birmingham East Campus to teach a physics class, I'll have a chance to load it onto YouTube once it gets loaded. Okay. All right, or onto the playlist once it's loaded. Okay, so let's go from current slide. Now let me say this. I was just explaining it to Justin, right? Okay. I don't know if you remember, on the YouTube videos, all my old videos are going to be at the top, and the new ones are going to be at the bottom of the playlist. So, and they just scroll up, and when I add a new one that covers something at the top, I'll take the old one off and put the new one on. That way, there's always the whole course out there, even if it's not this class. The whole course is there. Okay. Any questions before we get started? Okay. Well, let me get this stuff out of the way. I'll do, since you weren't here to hear it, the research paper, if I get it in today or tomorrow, the month of May, you get 2 bonus points, okay? Get it to me in June, you get 1 bonus point. In July, you just get your score, okay? So we'll go with that. So let me rearrange here. I say that because in one of my classes, I already got the research paper in. She gets her 2, okay? And also, this book has no PowerPoints with it, so there aren't any PPTs, but I record everything on the screen, ionizing pen right on it, and since it's projected, that gets recorded. My arm waving does not, okay? Just my voice, yes.
Yeah, after class, I do have some questions on Tuesday.
On what?
On the homework you assigned Tuesday.
Okay, in this class?
Yes, sir.
Okay, if you want to ask them now, we can.
So when it came to problem 15, or not 15, it was if you assigned right here on 17.
17?
Or no, not 17, 19. I'm sorry.
19.
It said D capital X over ET.
Okay.
Which are you supposed to do full right there? And then
All right, let me read it in a moment here. In this problem, verify that the indicated expression is an implicit solution, not explicit, but implicit solution of the given first-order differential equation. Find at least one explicit solution in each case. Well, okay, that means in this problem, 19 and 20. Okay, use a graphing utility to obtain the graph of the explicit solution. Now, if you don't have one, you don't have to do that part. Give an interval I of definition for each solution phi. Okay? Okay, so here's number 19. So if I'm doing something that you already know, stop. So this, let me get my pen set up. Okay. Okay. This is page 13. This is exercise 1.1. It started doing this yesterday like crazy, and then when I tightened this, it quit. Now it's doing it again. I don't know why. I think I do know why. When this wiggles and jiggles, and when it does, evidently, since it's closely connected to where the plug is, it creates a short or something. But they say to go in and repair it, it would take more than to buy me a new computer, and they don't want to buy me a new computer. So, yeah. Okay, so it flashes on and off, but it just about always comes back. All right, and this exercise at 1.1, and this is number 19. All right. And it's dx over dt, by dt, not over dt, is equal to x minus 1, that's a capital X, by the way, okay, times 1 minus 2x. Okay? All right, there's your differential equation. Here is the proposed solution, implicit solution, that log of 2x minus 1 over x minus 1, I can't write, is equal to t. Okay. That's a little bizarre in the fact that it's the dependent variable is in the function and the independent variable is by itself. Most of the time we write the dependent as a function of the independent. In this, the independent, because it's down here, is written as a function of the dependent. So obviously, I hope obviously you see that is what's going on. Now, what it says, the first thing it says to do, now, did you have a specific question or you want me to just sort of work through it?
I didn't know how to solve it, to be honest.
Say again?
I didn't know how to solve it.
Okay. All right. So it says first, verify that the indicated expression, the thing on the right, is an implicit solution of the given first-order differential equation, what's on the left. So what we want to do is take the derivative of this with respect to t. Okay? Now, there's a couple ways you can do it. You could do brute force now and try to do that one. That's going to involve, of course, the derivative of the log, which is not hard. But then you've got the chain rule, which is the derivative of the quotient, which is a mess, okay? And then move on from there. So the first thing I would do, because I'm lazy, you may be hard workers. Have you heard my theory on good mathematicians? Okay. My theory on good mathematicians is a good mathematician, and this hasn't been proven, this is just my little theory, I've never read it anywhere else. A good mathematician, I think, has to be just a little lazy, always trying to find the easiest way to do a problem. Okay, now do either of you qualify? Oh wow, I've got a bunch of good mathematicians in the class, that's good to see, okay. Now, but if you're a hard worker, you can still do it. I don't want to dissuade that. Okay. So what I would do is use the rule of logs and rewrite this as log of 2x minus 1. Tell me the next part. No, the log of a quotient. Oh, you don't know it, okay, is the difference of the logs. Okay? Now, let's see. I can't recall, I teach from so many different books. I can't recall if this one actually has these in an appendix or somewhere. I don't know if it does, but I know your calculus text probably does. I know it probably does. That's not very good cynicism. I think it probably does, or you can find it somewhere. It's the properties of principles of properties of logarithms. That the log of a quotient is the difference of the logs. I know you young guys have never even heard of a slide rule, right? Okay. Before, you'll think this is ancient history, but when I was in college, first year and beginning my second year, I had heard about the development of these things called handheld calculators, okay? But I'd never seen one. I'd heard they were in development. So before that, when we were trying to do large, complicated numerical operations, you used the slide rule. Now, adding and subtracting, you just do. I mean, that's not that bad. But multiplying and dividing large numbers, powers, and all this kind of stuff without a calculator was a task. So they had a thing called a slide rule. And a slide rule was the number scale was all in log scales. Okay? And what you would do for something that was multiplied, you would find the number on, it had a sliding scale in the middle and then fixed on the bottom. Find the number on the fixed scale, and then slide the slide over there and line up the 0 here, and then add the log of the number that you were multiplying, and then read down here, and then take the anti-log, and you had the answer. That's how you did complex calculation. Only had maybe 1, 2, or 3 digits precision, but that's all you lived with, okay? Couldn't do any more. And so basically, all of us knew that to multiply to the log of the product of 2 numbers is the sum of the logs. That's the whole principle of sum. Same thing here, the log of the difference of 2 numbers, of the quotient of 2 numbers, is the difference of the logs. So that's one of the rules of logarithm. Good thing to know, okay? Now, in this form, it's a lot easier to take a derivative because there's no quotient rule in it. I don't really care for quotient rule too much. So let's do it, okay? So what's the derivative of a log? 1 over whatever is inside that. So 2x minus 1. But then you got to take the derivative of what's inside. Chain rule, right? And the derivative of what's inside is? No, 2. 2. And then, because this is the dependent variable, you have a dx dt, because we're taking the derivative with respect to t. So that's the second part of the chain rule. Okay? Got it? Okay. Okay? Or second chain rule, I guess. Minus, and then what would you have there? 1 over x minus 1 times dx dt. Yeah, times 1 times dx dt. And that's equal to, and what's the derivative of t? Now, t is your independent variable. What's the derivative of t?
Would it be t prime? What?
1. That's the independent variable. Derivative of x, if x is an independent variable, is just 1, right? Okay, so that's equal to 1. That's an implicit differentiation of this problem. Okay? So what we do now is get the dx dt's together, okay? Because that's what you want separated here. So this is dx dt times 2 over 2x minus 1 minus 1 over x minus 1 is equal to 1. Agreed? Okay? Now, what I want to do here is to get this least common denominator and clean this up a little bit, okay? So this will be dx dt times, common denominator is 2x minus 1 times x minus 1. Okay? Now what we had to do, that's your denominator part, to get this over that, you need to multiply this numerator and denominator by x minus 1, right? So that down here will then be 2 times x minus 1, which will be 2x minus 2. Agreed? Okay. And then for this part, we need to multiply numerator and denominator by 2x minus 1, right? Right. To have that as a denominator. So that will be a minus 2x plus 1, right? Minus 2x plus 1. Now I'm skipping a few steps just because I don't have much room to write here. And this is equal to 1. Agreed so far? Let's clean up that numerator a little bit. And you see 2x minus 2x is 0. That disappears. And minus 2 times minus 2 plus 1 would be minus 1. So basically, I'm going to write it over here, dx dt times minus 1 over 2x minus 1 times x minus 1 is equal to 1. Right? All right. I want to isolate this because it's isolated here, right? So what I'm going to do is multiply by the reciprocal. Okay? But I notice there's no minus here, but I notice something else. They reverse the order of that. So if you change this to 1 minus 2x, that does away with the minus. Right? Okay. Clever of them, wasn't it? Sneaky is what I would call it. Okay. So we're going to do that, multiply both sides, and what do you have? dx dt is equal to multiply by the reciprocal of that when you change that around, and that's just 1 minus 2x, it'll show up in a minute, times x minus 1. And that's exactly what they have up there, but just in different order.
How come the 2x becomes a minus 2x?
Okay, because I was getting rid of the minus sign.
But how come the x minus 1 don't flip?
Okay, you could. You could have left this alone and swap that. It doesn't matter. You just do it one.
Oh, okay. I thought both.
Now, if you did them both, then that would be a minus times a minus would be a plus, and the minus sign stays. You're trying to get rid of that minus sign, so flip 1. Okay. So yeah, it would have been just as correct to do it the other way. 1 minus x and 2x minus 1. That would be another answer. Okay. So, we verified that is an implicit solution for this. It works, right? That was the first part of it. Okay? Now it says find at least one explicit solution, y is equal to phi of x in each case. And I guess that each case means number 19 and number 20. Okay? So we'll do it for 19. Find at least one explicit solution. Okay? Is that the part that gave you problem, or is this the part that gave you problems? Was this the clear part to you, or was this the part that you... Huh?
That's fine.
No. I mean, what was giving you problems with the homework? This one? Even how to start? Okay. So this gives you at least the first part of the answer. Okay, the next part, find at least one explicit solution, y is equal to phi of x in each case. Okay? Now there's a problem with that. It should be in this problem phi of t, not phi of x. So that's a little misleading there. Okay. All right. Let me just make a suggestion to you. I'm going to cheat a little bit and check and make sure I'm going down the right path in the back, if they even have the answer back here. This is number 19 and 1.1. I don't want to lead you astray, so let's 19.
They got the answer like weird. X equals
Wow.
e to t minus 1 over e to t minus 2.
Yeah. Okay, I didn't know that you were going to take it that far, but it's certainly okay to do. So they didn't really answer the second part. In fact, it has nothing to do with it. Okay. Okay. I'm trying to do this in a way that's consistent with what we've covered so far, and frankly, what we've done so far, I don't see how they can do that solution just based on what we have so far. But since they asked for it and it's in the back, I'll show you, even though we haven't done this yet. So this is really how I would like to teach differential equations, but we have to use this, or we use this book. So I'm going to erase most of this. This showed that that was true, okay? Now, the second part, finding an explicit solution, and I really don't know how they got this without doing something well beyond what we've done so far. This shows it works, but I'll take the time now to show you how to solve these, which is what I would rather be doing than doing this chapter 1. But I think, evidently, they think chapter 1 is necessary, so I will go along with them. But this, to me, is where we should really be doing, is solving differential equations. So I'll give you the technique. Okay? We will do this in chapter 2, but I'll go on and do it now. What technique I'm going to use is the one called separation of variables. Okay? Have you heard of that before? Okay, well, here's what it means. What I'm going to do first, and the book actually uses this terminology, but it drives mathematicians crazy, multiply both sides by dt. Really, the better way to say it is write it in differential form, which would be dx is equal to x minus 1 times 1 minus 2x dt, which looks like you just multiply both sides by dt, which is fine to think of it that way, but that's actually written in differential form. Well, now you have the dx over here and the dt over here. Okay? So let's move the x's with here, which means we go back and divide them back again. Okay? So maybe if I had left the other thing up there, that would have been a better place to start. So we divide both sides by x minus 1 times 1 minus 2x, x minus 1 times 1 minus 2x. Okay? This goes away. Okay? Now what we do is integrate both sides. All that's left over here is just dt. Okay? Now, that's not a super easy integration over here, but it is straightforward. Does anyone remember how to do one like this? This requires Cal 2.
You would do, what's it called? It's the one where you do A over B.
Yeah, partial fractions.
Partial decomposition.
Okay. This book calls them, or the book we're in now calls them partial fractions. Yeah, that's what you're doing. And you're decomposing the function that way, so I can see why they would call it that. So I'm going to write this as 1 over x minus 1 times 1 minus, I can't write, 1 minus 2x equal to some a over x minus 1 plus some b over 1 minus 2x. By that, we're going to decompose this and write it as a sum. Now, here's the trick to make it easy. Multiply everything on both sides by this denominator. Multiply by x, because this is an equation now, you can multiply both sides by the same thing. 1 minus 2x. Multiply this by x minus 1 times 1 minus 2x. If I had planned ahead, I would have given myself more room. Multiply this by x minus 1 times 1 minus 2x. Okay? Well, over here, everything goes out except the 1. Right? Over here, the x minus 1's go out. And on this one, the 1 minus 2x goes out. So here you have 1 is equal to a times 1 minus 2x plus b times x minus 1. Okay? Now that should be true for all x's in the world, right? Okay with that? Okay. So it should also be true for x equal 1. Now why did I choose that? Because this is going to disappear then, right? Second term here. So we'll use it for x equal 1. And what do you have then? Over here there's no x's, so I'm going to go to the top over here. 1 is equal to a times 1 minus 2 times 1 is 2, so that's a minus a, right? I just plugged in x equal 1. Do you buy that? Okay, and when I plug in x equal 1 there, that goes to 0. So this tells me that a is equal to negative 1. Well, that's nice, isn't it? Okay, now we're going to do the same type procedure to get the b. But this time we're going to let, this is going to be a little trickier here, this time we're going to let x equal 1/2. That will wipe out and make this 0, won't it?
Could we just plug in the negative for a equals negative 1?
You could do that, okay? It's easier doing it this way, and I'm lazy, okay? But yeah, you could do it the other way. You're absolutely right. But if you put x equal 1/2, then when you plug that in here, you get 1 minus 2 times 1/2 is 1. That goes to 0. And then this will be 1 is equal to, and 1/2 minus 1 is minus 1/2, minus 1/2 b. Correct me if I'm wrong. I think that's right. So this means, implies that b is equal to minus 2. See, that's pretty easy to do. You could do it the other way too, and that's perfectly fine. It's correct, and it's not that hard either. So it's okay. Okay? Got it?
Yes, sir.
Okay. Now we go back and rewrite our integral here. The integral of this thing is now going to be minus 1 over x minus 1. That's your a part right here. That's where I'm trying to find it right there. Dx minus 2 times the integral. Should have left that in there. I think I should have, of dx over 1 minus 2x. Okay? And that is equal to the antiderivative of t, of dt, which is just t. Okay. And don't worry about your c's yet. You know, plus c's, we're going to get to those in a second. Okay? Now, what was that? Okay. Antiderivative of 1 over x, 1 minus x?
It's just ln of x minus 1.
Okay.
Negative.
Okay. Negative ln of x minus 1. You know, I'm just going in circles here. We're going to come back to our original, no, we're going to come back to the solution we got before. So it wasn't necessary to do this. This just gives you the solution we got before. Sorry about this, because this is going to, because of minus 2 here and minus 2 here, this is going to be positive. That's going to be on the numerator, this is going to be in the denominator, and that is exactly what we had before. Yeah. I'm just showing you how they got that. Sorry about that. Okay. So, sorry. I was showing you how they got it, but that's not what they were asking for. I was thinking we would come up with an explicit solution, but we really didn't. So what we need to do is go back. Sorry about that. But it showed you separation of variables and how we proceed. but it wasn't going to get us anywhere new. It's going to take us right back to where we were, and it was just a lot of killed time there. So sorry about that. Not being very good mathematician here. Okay. Worked too hard to get nothing. Okay. Now, so here's your answer. The log of 2x minus 1 over x minus 1 is equal to t. Okay. So we want to come up with, it's not a y, it's a capital X is some phi of t. They say y is phi of x. That's for the second one, number 20. It's not for the first one. Okay. So, what we're going to do, we're trying to solve for x. I'm sorry, I took you down a path that we didn't need to go. Well, how do you solve for x here? One thing you got to do is undo the log. What does that for? E. Okay. Let's take the e of both sides. Okay. E of log of 2x minus 1 over x minus 1 is equal to e to the t. Buy it? Okay. And e of a log is just going to be simply 2x minus 1 over x minus 1 is equal to e to the t. Okay? We still need to solve for x. So let's multiply both sides of this by x minus 1. Okay? Wiping that one out, and you get 2x minus 1 is equal to e to the t times x minus 1. Okay? We're trying to solve for x. That's what we're gunning for here. So let's do this first. This will be x times e to the t minus e to the t. Right? You just distribute across there. Okay? Now, let's get the x terms together and the non-x terms together. So we're going to subtract the x times e to the t from both sides. And we'll add 1 to both sides. Okay? Now I need more room. Okay? Can I erase that line up here? Here? Okay. It's how we got there, but we don't need it anymore, so I'll go on and erase it. Okay. I'm writing too big here. So here's what we've got. 2x minus x to the e to the t is equal to 1 minus e to the t. Okay? Okay. Over here, we had 2x. These two terms went away. 2x minus x times e to the t here. And here, because I don't like leading off with a minus, I put 1 in front. 1 minus e to the t there. Yeah. Got it? Sir. Okay. Yeah, I can tell you convinced. Okay. We're trying to solve for x, so let's factor out the x. And that would be x times 2 minus e to the t is equal to 1 minus e to the t. Got it? All right. And now all we do is divide both sides by 2 minus e to the t. Okay, and that's ugly down there, so I'm going to write it here. X is equal to, these go away, 1 minus e to the t over 2 minus e to the t. Now, I don't know if that's how they wrote the answer in the back. Let me see. I need to mark my place back here. Is it? Yes, sir. Okay. Wow. Okay. Wrong page. Here we go. 19. Yeah. Now, that's the first part. That's Second part of our question, right? A solution, x is a function of t. They didn't quite say it right. They said find at least one explicit solution, y is phi of x, but in this problem, it's x is phi of t. And there it is. X is a function of t.
So would you plug that x into the original problem, the ln of 2x minus 1?
Yeah, if you do all that, you should get t.
Okay.
I'll leave that to you to do.
Yeah.
Okay. All right. Now, there is one more thing. It says use a thing to do a graph, so if you got a graphing calculator, do it. If you don't, I don't care. It says give an interval I for the definition of x solution of phi. Not phi, but x. Okay? So, what will be the, what do they call it? Interval I of definition. I can't remember. In other words, a domain. Okay? Well, here's the issue, folks. What can you... Here is your solution. I mean, yeah, this is the solution you're dealing with. What do we know about logs? Where are they defined? See, looking at this, any t seems like it should work because exponential functions defined everywhere. Oh, well, no, not quite. Okay? Here we have an issue here. Let's deal with this one. I think that'll take care of this one. Okay? What's the issue here? This can't be 0, right? You can never divide by 0. So, in other words, 2 minus e to the t cannot equal 0. By that? Okay? So that means 2 cannot equal e to the t. By that? Okay? Then take the log of both sides, and you get log 2 cannot equal t. I say cannot equal and don't write. Okay. So, there is our interval of definition. It can go from negative infinity up to log 2, or it can be anywhere between log 2 and positive infinity. It just can't be log 2, okay? Now, it can't be anything else. The intervals have either got to be something in here or something in here. It can't be both. Whatever your condition is, that will determine. I think that's what they had in the back too, right? Interval of
Yes.
definition.
Negative infinity.
Is that right?
Yes, sir.
So that's the whole part. Only thing we didn't do was do the graphing, and I don't have a graphing calculator. Okay. Does that answer your question?
Yes, sir.
Okay, good deal. Any others? All right. Good to get that kind of stuff done now rather than wait till test time and say, how do you do this? Okay. All right. So last time we had talked about families of solutions, and they also mentioned a solution of a differential equation that is free of parameters is called a particular solution. Okay? So example 8, that's where we left off, or at least my memory was. Is that right? You were here last time, Nolan, right? Example 8?
We got to, last thing I got, we did families of solutions.
Family of solution, particular solution, right?
Yeah, solution 3 is a particular solution.
What's that?
Yeah.
Okay.
We did like the G, X, Y, C.
I can't hear it. So.
G, X, Y, C, and then F of X, Y, and then Y prime, Y double prime, and then it says N parameter system.
Okay.
Sorry.
All right. So I think we're at example 8 on page 9. Does that seem right to you? Have you got the book there?
Yes, sir.
Is that about it? Okay, so let's do example 8 on page 9. The A part. This is example 8, page 9. Okay. A part. For all real values of C, the one parameter family, y is equal to cx minus x cosine x is an explicit solution for the linear first order differential. So this is a solution of xy prime minus y is equal to x squared sine x. Okay, there's the differential equation. This time they gave us a solution first and then did that. Okay. And it says on the interval minus infinity to infinity. Okay. That's really hard to read. I was trying to cram it on the page, but it makes it too hard to read. So, on minus infinity to infinity. Okay. That's the interval of definition, or whatever you want to call it. Okay. Now it says verify. So that basically is doing the same thing we did before. Okay. We have this is the solution. We want to verify that it solves that equation. So what would we do? What's the Jesus answer?
Derivative.
Take a derivative. Okay, now you probably don't understand what I mean by that, do you? I gave this dumb example. I've been to several churches that early in the service they have the children's church. Okay, and they'll bring all the kids up front. And then usually a pastor or somebody, a honcho up there will do, and they always like to start with a question. And they'll ask, okay, kiddies, and ask some question. Of course, the kids look there, scared to death, don't want to give a wrong answer, don't have any idea what he's talking about or she's talking about, just sit there. And finally, some little guy in the back, usually it's a boy, will say, Jesus, because he figures, whatever they ask you in church, Jesus is a good answer, right? So I call this the Jesus answer. When you can't think of anything else to do, take a derivative. Okay. So in this class, that's not a bad first guess anyway. Let's take a derivative. So let's take y prime. And, of course, why do we want y prime? Because it's in this differential equation there. So if we know what y prime is, we can plug it in. Okay? All right. So what's y prime?
It's going to be y prime is going to equal c.
C. That's yes in Spanish. Okay, what? Minus?
Or actually plus.
What's that?
Wait. Would you do chain rule or
Product rule.
Product rule. All right, that's going to be negative 1 times cosine x.
Okay.
And it's going to be plus sine x times negative x.
Not negative x, x.
Negative.
It's x. Okay. Okay. You did derivative of that is a c. Got it. Derivative of this is, okay, let's just put the minus up. Okay. Maybe, were you just taking the minus out front?
I just let them, I thought it was a negative x.
Okay.
X.
All right.
That's why I did it.
Here's the deal, folks. Here's another little theory. The only reason we have negative numbers is to trip you up. Okay? Minus signs are only there to make you fall down. So be careful with the signs. So here's what I'm going to do here. Let's rewrite this as just that. Okay? And that means we're going to do the product rule, and I hate to erase it because I'm going to write it right back down again. Let's just take the derivative of this with the minus sign out front. Okay? So, forget about the minus sign. We're just taking the product rule of this. And what would that be?
1 times negative sine.
Negative sine x.
Times x.
Second.
It would be negative sine x times x.
Wait.
X, right? You do the
Okay, wait. Okay, right. Okay, I'm sorry. I was trying to go by what you said, and I got lost. Okay, I didn't hear everything you said. Okay, negative x times the sine of x. By, okay? Plus
1
cosine x. Okay. Now, let's distribute the minus sign across, and you get y prime is equal to c plus x sine x minus cosine x. Is that what you said before?
Yes, sir.
Okay, all right. All right, I was thinking, no, I can't remember what you said before, but that is the answer, okay? Now that we know what y prime is and what y is, let's plug them in there and see if we get an identity. So this is going to be x times y prime, which will be c plus x sine x minus cosine x minus y, which is cx. Now I'm going to take off my parentheses. They weren't there in the beginning, so let me take them off now. Okay. Minus x cosine x. Okay? Now, the question is this equal to x squared sine x? We don't know. We're not there yet. Okay? So let's see what we get here. Okay? All right. Let's multiply through here, and what we get is x times c, which I think I'm going to rewrite as c times x. That just looks a little nicer, doesn't it? Okay. cx plus x squared sine x, that's looking good, minus x cosine x. Y'all agree so far?
Yes, sir.
Okay. Minus what? You tell me the next part.
CX
Cx plus x cosine x. Is that equal to x squared sine x? Okay. It'll come back in a second. Now what can we do here? CX's go away, and the x cosine x's go away, and look at what we got. Sure enough, it's no question mark anymore. That's for certain. So we have now verified that that is a solution of that differential equation, right? Done. Okay? By the way, y'all have to help me keep track of time. I can just keep talking forever. And I don't have any more classes till 4:30, so stop me before 4:30, okay? Okay. I'll get hungry by then anyway. Okay, so we've done the first part, we verified. Okay? Figure 113 shows the graphs of some particular solutions of the family for the choices of C. Okay? The solution y is equal to x cosine x is the blue one there, and that's the particular solution corresponding to C is equal to 0. Now they did all the talking and work there. They didn't show you anything. Here you really almost need a graphing calculator to plug. Well, even with a graphing calculator, I don't know how you would do it. Well, there's your solution. And what you would do was plug it in with C equals 0, C equal 1, C equal 2, C equal 3, negative 1, negative 2, negative 3, all those. Plug those in and graph them on the same graph, as many as your graphing calculator can do, and you'll produce something, hopefully, that looks like this. And they said a particular solution was choosing some value for C. Well, they used the simplest one of my favorites, is C is equal to 0, and that gave you y is equal to x cosine x, and that would be your blue curve here. and C is equal to 0. Now, so what is a particular solution? It's a solution. There's tons of solutions out there, infinite number of solutions. But pick a C, any C. You could have chosen 3,444,817. Plug that in there, that would be a particular solution. It's free of the parameter, okay? And that's one of them. That's the easiest one, to C is equal to 0. Okay. But without a graphing device, I can't show it to you, but I can show it to you there in the book. Let's go to the B. I think it might take more room, so I'm going to erase this. Does anyone need it any longer?
No, sir.
Okay. So we'll erase that, and let's do the B part. Okay? The two-parameter family, y is equal to C1 e to the x plus C2 x e to the x is an explicit solution for the linear second-order equation y double prime minus 2y prime plus y is equal to 0. Okay? All right. Oh, this is one we've done before. Back in example 5, they said. I had forgotten that. They want us to verify this. So how do you verify it? Ha ha! Good answer. Y prime is equal to?
Is C a constant?
C is a constant. Both C's are constants.
Okay, so then there's e to the x.
Okay, C1 e to the x, right?
I thought it was a constant. I thought constants go away.
Okay. They do, but e to the x doesn't.
I know. I was saying, like, I thought the C1, or it applies to e to the x.
Okay, wait. The first term is C1 e to the x. Now, if that had been C1x, the derivative of it would have been C1, right? Okay. C1 e to the x, derivative, the C1 is just a constant. Write it down, C1. And then what's the derivative of e to the x? E to the x. It's C1 times e to the x. Aren't we agreeing?
Yes, sir.
Yeah, okay, good. Okay? Plus, now here we have a product rule. C2. Now let's do the product rule. And if you want to do it separate from the C2, we can.
E to the x.
E to the x. Plus.
X. X e to the x.
X e to the x. You're absolutely right. And if you straighten that out, clear the parentheses, or distribute, whatever you want to call it, C1 e to the x plus C2 e to the x plus x e to the x. Okay? There's your y prime. Oops. Whoops. You let me get away with it. Almost. Distribute that C2 across. I forgot to do that. Okay? Next. Now, the question is, you want to simplify that a little bit. I don't know. Seems like it would be just as easy to go from here. Let's do it. So what you do next? Yeah, take a derivative, y double prime. And that will be C1 e to the x plus C2 e to the x C2 e to the x. Is that what you said? All right. C2 x e to the x. Think we got them all? This one we can simplify some, and let's do it. That's C1 e to the x plus 2 C2 e to the x plus C2 x e to the x. Buy that?
Yes.
Okay, so what do we do now?
We just
Plug that into here. So your y double prime is c1 e to the x plus 2c2 e to the x plus c2 x e to the x. Got that done. Minus 2 times y1. And here's your y1. So let's do that. Minus 2 times there's your y1. Right there. So that would be, your y prime. I don't know why I'm saying y1. 2 times, see it there? Plug it in. What will be the first term?
C1 e to the x.
Okay, minus 2, c1 e to the x.
Plus C2
No,
e to the x.
okay, you're doing it in parentheses?
Yes, sir.
Okay, that's fine. I'm sorry. I couldn't hear the parentheses there. Okay.
I don't know where to go. I just had them all lined up.
Okay, let me go back and erase then. Well, no, I think I'm okay. I think I'm perfectly okay. So let's go back to the pen. Put parentheses here, plus here. Okay, go on. Nope, whoop. I did put it in the wrong place. There, okay. Plus c2 e to the x plus c2x e to the x. Okay? Plus, plug in the y. What's your y?
C1 to the x, C2 to x,
Okay. The question is this equal to 0? Well, let's clear the parentheses there, and you get c1 e to the x plus 2c2 e to the x plus c2 x e to the x minus 2c1 e to the x. Keep me going here.
Negative 2c2 e to the x minus 2c2x ex plus c1 dx plus c2x dx.
Is that equal to 0? Wow, that's a whole lot to equal 0, isn't it? So let's see what we got. Let's look at our c1 e to the x. There's 1 there. There's minus 2 there. But there's a plus 1 there. So 1 and 1 is?
2.
2 minus 2 is 0. So those go away. That one, and that one go away. Let's do our c2 e to the x. You got 2 of them here, and you got minus 2 of them there. Those go away. Those add to 0. This one and this one add to 0. All right, let's do our c2x e to the x. You have 1 there, you have 1 there, you have minus 2 there, they go to 0. So sure enough, we've just verified that that's equal to 0. Okay? Now, without having a graphing calculator, I'm just going to use the books here. And of course, people at home can't see this because that's not being projected. I'm just putting it here so you can see it. Page to be in class, right? Okay. So, if you were to draw this, these are the solution curves for various C's. C1s and C2s, I think. And for 7 of the double infinity of solution. Oh yeah, what they mean is you have an infinite number of C1s and an infinite number of C2s. What do they mean by double infinities? Okay, that's what they mean. Okay, of solutions. The solution curves in red, green, blue are the graphs of, and they give various ones. So since that's our solution, if you use C1 equal 1 and C2 equal 1, then that's going to be, oh, they don't show that one, sorry about that. C1 equals 0 and C2 is equal to 5. That would be the, why they chose that, I don't know. That would be 5x e to the x. That would be the red curve here, okay? If you choose C1's 3 and C2's 0, why that, I don't know. But then you'd have 3e to the x plus 0. That is simply an exponential function. That's the green one, they say. Yeah, there it is. That's just your exponential function heading off that way. And then the third one is 5e to the x, where C1 is 5 and C2 is 2. That would happen to be the blue one that does like that. So I don't know what you were supposed to learn from that. What we did, we verified that was the solution. To me, that's all we got from it. A particular solution is one in which you choose certain C's, values for C, and that comes up with a unique solution. A solution. One of many solutions. So I can't say unique solution. One of an infinite number. In fact, they say a double infinite number of solutions, because you have an infinite number of C1s, an infinite number of C2s. Choose whichever you choose. Okay? So those are particular solutions because you've chosen a C. Now later we're going to use particular solutions when you have a solution that's completely independent of these parametered solutions. But they're not doing that yet. I thought they were, and I wondered how in the world they were going to do that this soon. Okay? And sometimes a differential equation possesses, this is the top of page 10, a solution that is not a member of the family. This is the one I thought they were going to talk about. And these they call singular solutions. Okay? And it's going to take us back to something we did earlier. Okay. What is it right now? 9:45-ish?
9:42.
Okay. And we go till 10:45, don't we? Yeah, I believe so. Okay. We got plenty of time. When we did that problem at the beginning, it threw me off on time. So no, I want to do them. That's better to do them now than trying to find them later. Okay. But I was not sure of where we were time-wise. Okay. Let me erase this. Y'all fine with it? Erase?
Yes, sir.
Okay. It's gone. Okay. Earlier we found that y is equal to 1/16 x to the 4th. And y is equal to 0 were both solutions of this differential equation. dy dx is equal to xy to the 1/2. Okay? On the interval minus infinity to infinity. Okay? That's an ugly infinity. You have to live with it. Okay. They say that later in section 2.2, and this is when we get into separation of variables, we'll find that there is a one-parameter family of solutions. Y is equal to 1/4 x squared plus c squared. Okay? Now, Earlier we found that this was the solution to that. If you go back in your notes, that was one of the first examples we did. Okay? May not have been the first, but one of those. Okay? But we also know that's the solution. Okay? Now, later we'll do and come up, this is your family of solutions. Well, it's obvious, I hope, that when C is equal to 0, that's what you get for your first one. When C is equal to 0, 1/4 x squared squared, C is 0, is going to be 1/16 x to the 4th. There it is. So that particular solution is one of your family of solutions. But can you find a C that's going to produce y is equal to 0? No matter what C you put there, y is not equal to 0. So that one's called a singular solution. It is also particular because it doesn't have any C's in it, but it's a singular solution. It cannot come from your family of solutions. So that's what they're talking about at the top of the page there. Okay? Now, the next thing they hit is, in all the preceding examples, we use x and y to denote independent and dependent variables respectively, x being independent, y dependent. But you should become accustomed to seeing and working with other symbols to denote those variables, as if they haven't done that before. For example, you could use the independent variable t, dependent variable x. Y'all are used to that too, aren't you? There's nothing new there. All right, so we're going to use different symbols in example 9. So this is, the purpose is sort of nebulous, but the practice is worth something. Here's a function. X is equal to C1 cosine 4t. And another solution, x equals C2 sine 4t. Okay? Where C1 and C2 are arbitrary constants or parameters. They claim these are both solutions of this linear differential equation. X double prime plus 16x, 16x is equal to 0. Now, if that's all you had, you don't even know what the independent variable is. You know this is second derivative of x with respect to something, and there's plus 16x as a function of something, but we don't know what the something is. They just tell you x is a function of t. Okay? Now, I think what they're going to do, though they didn't say it, let's see if that's indeed true. Let's take derivatives. Okay? So what's your, for the first x here, x is equal to, or x prime is equal to what?
C1.
Say again? C1, yeah, that's fine.
Sine. Negative.
Yeah, negative. Sine 4t. One other little detail.
Oh, and we had the other one.
Say again?
Oh, wait, we did chain rule.
Chain rule.
So it'd be
4, yeah. So minus 4, C1, sine 4t. Let's do x double prime.
It's going to be
minus 4 C1 cosine 4t times the 4 again, right? So that becomes negative 16 C1 cosine 4t. Okay? Now, if you take this x double prime minus 16 C1 cosine 4t plus 16 times C1 cosine 4t, which is your x up there, right? You get 0. See? This one plus 16 times that one is exactly 0, right? This, that's your x double prime, plus 16 times that. This is minus 16c1 cosine 4t, plus 16 times c1, that's equal to 0, right? When you plug it in.
So both x's would equal 0?
I'm sorry?
Both x's would equal 0?
No, okay, we just did this one. Okay, let's do that one now. You're jumping ahead, which is good. So what's your x prime here?
That would be C2, sorry, cosine 4t. There's a 4 out.
With a 4 outside, okay. And what's your x double prime?
That's going to be negative 16 C2 sine 4t.
Somehow I got a CO2 in there. I must be in chemistry class. I don't know where that came from. Let's get that cleaned up. Negative 16C2 cosine 4t. And sure enough, when you take this and, did I write cosine? Did you tell me cosine? Okay, what goes there? Sine. Okay. I don't know. I was so focused on where I got the CO2, but never mind. Okay. If you take this one and add 16 times that one, you come up with 0. So both of these are solutions. Okay. Now, we verified that. So we've done what they did there. Now, here's the next part. We verified that both of those are, and by the way, if you haven't picked up on this yet, remember when we had the first one in example 8a? It just had a y prime, and we wound up with just one independent variable, parameter, right? But when we did the b part, we had y double prime, we had 2 parameters. This one, number 9, we have x double prime, we have 2 parameters. Get the gist? The number, the degree, the order of the differential equation is an indication of how many parameters you should have. If it's the first order, you're going to have 1 independent parameter. Second order, 2. Third order, 3. Fifth order, 5. You know, so expect that. Okay. But here's something else. Just because these 2 are solutions, and you have to have, because you have a second order, you've got to have 2 independent solutions. Here's something else. The combination of these, x equal c1 cosine 4t plus c2 sine 4t, that's a solution, okay? I don't need the equal sign there, okay? And because if you take the derivative of this term is completely independent of that. You go down and you get the same thing you did here, say the same thing you get here, and they still add to 0. So anytime you have 2 solutions, the linear combination of those is also a solution. That's called the superposition principle. They haven't named it yet, but they will be calling it that later. Okay? All right. Now, have you added the class?
Huh?
Have you added differential equations?
Yeah.
Huh?
Yeah.
You have? Okay, because you weren't on my roll before. But it's great to have you, but I was just wondering, did you recently add? Huh?
I had this class already. I just had to go to the other campus because there was a mix-up, and I had to decide like what to do.
Right. So you are registered for the class.
Yeah.
Okay. Well, come on, sit down. But I just wanted to let you know I printed this roll. What was it? Back on the 23rd. Were you registered then?
Yeah, I should have.
Well, you might want to check and make sure, but let's go on and sit down. We'll have class today. Granville, I'm trying to remember your name. Daniel, right?
Yeah.
You still go by Daniel?
Yeah.
Okay, so you're adding today too. But you might want to check after class today, which isn't too much longer, and make sure they got you on the roll. It's about 45 minutes from now, right? Okay. And it is differential equations that you think you're at.
Yeah.
Okay, yeah, that's the right class then. Okay. We're in section 1.1 on page 10. I don't know if you got a book yet, but...
Do you have the code part yet? Or
I'm sorry?
Do you have the code for the book yet? Or?
I think you can, if you're registered for the course, I think you can use, I don't have the code yet, but I think when you register, you get so many free weeks because you're in it, aren't you? Or
Yeah, you just buy Cengage.
what's that?
You just buy Cengage and then just look at the book.
Yeah. So if you register for the class, you can probably access it. I've got to get the code, so after the grace period's over with, that'll keep you in it, you know, but I don't have that code yet because I thought the class wasn't going to make, so I didn't set it up for it. But if you got, you know, you can go, what, you went to Cengage, did you go to Cengage Unlimited?
I had to buy Cengage for chemistry, but I bought Cengage and you just look up the book.
Right, okay.
On the syllabus, you gave us the link. I mean, not the link, but you just gave the title of the book, and so I just
Right.
copied and pasted on the search.
So you did the Cengage Unlimited, yeah, and so $120 you got all the books. Is that what you got? Okay. If you have, then you can access the book. You know. Okay. All right. But this is example 10, last example in section 1.1. Okay. Let me go to a clean page here. Any questions on this one before we leave? Okay. So the class is still growing. 6 students now. Good deal. The one-parameter family of solutions of a quartic monomial functions, boy, that's nice, y is equal to cx to the fourth, quartic means the fourth order, is an explicit solution of the linear differential first order equation xy prime minus 4y is equal to 0. Okay? On the interval minus infinity to infinity. Okay? It says verify, so let's do it. How would you verify that? Take a derivative. Perfect. Okay? Y prime is equal to? This is example 10. Is that not what yours shows? Okay.
We're good. Sorry, my book just froze.
I'm sorry.
We're good.
Okay. So what's the first derivative? 4 c second x to the third. Perfect. And what do we do with that? Plug it in, plug it in. So that'll be x times y prime is 4c x cubed minus 4, and what's the y? C x to the fourth. Supposedly that's equal to 0. I think that's pretty obvious. On this one, what do you get? 4c x to the fourth minus 4c x to the fourth. Sure enough, that is equal to 0. Okay? So we verified it. And that should be for any x anywhere. Okay? Now, here's what they're doing with this. It's all true, but I just don't see the purpose of doing this now, but they're doing it. Now, if you use C equal to 1, that's this blue curve. If C is equal to 1, that's that quartic solution. It looks like a parabola, but it's flatter in the middle and goes up steeper on the edges. If you use C equal minus 1, then you get the mirror across the x-axis, and you get it just flipped over. Okay? Now, what they show here is if you were to take C equal minus 1 for all x is less than 0, you would do the red part, and then for C greater than 0, for x greater than 0, do the upper part. Then you wind up with a solution that looks like that. Okay? So there's a piecewise solution, and why? Well, the only reason I can think of why, these neither one are one-to-one functions, whereas that one is. But what difference does that make now? It's not really clear. Okay, so sure, you can do this. And so you can have y is equal to minus x to the fourth for x less than 0 and positive x to the fourth for x greater than 0. You have a continuous, it's a piecewise defined function, but it's a continuous function, and it satisfies that differential equation. So, fine. Even though you only have one C, you're using two different values to define two different pieces of it. Yay. Okay, I'm glad they showed us that. All right. I really don't see the point of it, but it's true. It's obviously true. Up to this point, we've been discussing single differential equations containing one unknown function. But often in theory, as well as in many applications, we must deal with systems of differential equation, and that's just like a system of equations. You have dx dt is equal to some f of x, t, x, and y, and dy dt would be some function g of t, x, and y. A solution of the system, of that system of equations, would be some functions x equal phi1 of t, and y is equal to phi2 of t, defined on a common interval that satisfies each equation, blah, blah, blah. They just tell us that. We're not really going to do anything with it. So don't sweat it. Okay. Now we get to these things. And the first time I taught this course, I thought I had to go through and do all the remarks here, because that was in the thing. Actually, this is just, I don't know what they're there for. Some of them follow very directly from what we've just done. Some of them seem like they're just outer space. And they talk about integral defined functions. They talk about non-elementary functions. They talk about all these things, but they really don't do anything with it. They're just sort of thrown in there. Okay, on the next page it continues, and I was trying to find some thread of reasoning that brought all these things together. I haven't found them, so I sort of skipped them. But not a bad idea to read, and especially pay attention to what the bold words are. Sometimes maybe even the italicized. But if we go back to what we were talking about before, that the superposition, adding the different solutions together, linear combinations, that usually gives you what you call the general solution. So that's on the next page. When we need them, we're going to get to these terms. So don't sweat them now. I can't figure out why they put them in here. It just seems like something to boggle you. Okay. And the first time I did it, that's all it did was boggle me. And I saw we never used them, so I thought, why did I go through all that pain and agony trying to make this make sense with the other? It's there. Well, now exercises 1.1, you've done some of these. Any of the odds that are in the answers in the back of the book, 1 through 7, then do number 9, either 11 or 13, 15 or 17, and then 19. We did 19 earlier in class, so go back and review that if you weren't here. Either 21 or 23, either 25 or 27. Here's a piecewise defined function like we just saw. That's number 29. Then you can do either 31 or 33. Now, these are if they have the answers in the back. If they don't sweat them. Do number 35 if its answer's in the back, either 37 or 39 if its answer's in the back, and then 41 if its answer's in the back. Okay? The discussion problems, you can read through those and think about them, but in general, I do not find that those have answers in the back, so you don't have to worry with that. But it's not a bad idea to look at them. For instance, number 51 talks about the folia of Descartes. Well, there's two potential paper topics, at least. One is, who in the world is Descartes? You could write on him if you wanted to. Or, how did he come up with this folia of Descartes? Okay? Or, how do you use this folia of Descartes? You may want to find out it's in your field of study. Or you may find out it's not, you couldn't care less. Yes?
You said, what was his name? The person who made the folia?
Descartes. D-E-S-C-A-R-T-E-S. Rene Descartes. D-E-S-C-A-R-T-E-S. And the folia is spelled F-O-L-I-A. So looking at these may give you ideas for paper topics, or you may actually think about what they're discussing here. But I'm more interested in, let's moving to 1.2. Yes.
His name again?
D-E-S-C-A-R-T-E-S. Descartes. His first name is Rene, R-E-N-E. Okay, Rene Descartes. Anyone know anything in the room named after him? The Cartesian coordinate system. He's the one that came up with the XY plane and how to graph functions. He was the one who had taken geometry, which was considered completely separate from mathematics, and brought them together. The XY plane enables you to draw the shapes and give equations to them. So that brought geometry and algebra together into one family, mostly by Descartes. Descartes was also a very famous philosopher. You may have heard this phrase before, I think, therefore I am. That's him. So he was quite a thinker, so he was. Okay? He was big time. Okay. So if you're interested in that, he's a potential paper topic. Or any of those things. His development of the Cartesian coordinate system, that would be okay too. All right. Ready for 1.2? Okay. Now, 1.2 is introducing us to a type of problem that's called an initial value problem. And it's an okay name, but sometimes it's a little misleading. Because when I think of initial value, I think t equals 0. I mean, being a physicist, that comes to my mind. But the variable doesn't have to be t, and it doesn't have to have the value 0. It just means you know some first value. That's what they mean by initial value. You know some value. Okay? So we often are interested in problems in which we seek a solution, y of x, of a differential equation, but you already know most of the differential equations have infinite number of solutions. So if you know one value that's going to need to be solved by that, that's your initial value. It doesn't have to be where t is equal to 0 or something like that, but if you know one value, then you can determine which one of those infinite number of curves you want to use. Okay? We've been doing those already when I've shown you the picture. This is where c is equal to 0. They didn't say that's what we're doing, but we we're choosing one value. Okay. So, if this is your problem, it says solve d, the nth derivative of y with respect to x n times, and writing it in that, what do we call this, the general form or something like that. No. They use this term, and it's not really all that important, but I'm trying to remember it anyway. Yes. This is called the normal form. The other was called the general form. This is called the normal form. That some function, this nth derivative of y with respect to x n times, is some function of x, of y prime, of y double prime, dot, 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 up to y to the n minus first derivative. Okay? In general form, we usually use the capital F, and we include all those and this one on the end and set that equal to 0. It's just two different ways to write the same problem without writing the problem, writing it in sort of generic form. Okay? Now, if you have the nth derivative, okay, then you will need, if you're going a particular solution, you're going to have n conditions. Okay? So we say it's subject to, okay, y at x0 is equal to y0. Now, don't let the subscripts confuse you. It's just saying you have some value, x, and at that value you know y, and we're just going to call that x0. At that same value, we know that y prime at x0 is equal to y1, just is some value. Y double prime at that same value x0 is equal to y2, let's say. They're just representing the various things here. And you keep on going, dot, 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 up until you get to the y to the n minus first derivative at x0. And then this will be, if you'll notice your, yes?
What is that on the y0 between the y prime? Is it a semicolon?
No, that's a y prime.
No. Between the y prime and the y0.
Oh, yeah, I put a semicolon. Yeah, I put commas the rest.
I understand.
Yeah, I'm sorry.
No, that's fine.
Okay.
I was thinking I or semicolon.
Okay. I'm going to have to watch him. You know, he's too particular. I'm going to have you grading the research papers, okay? It looks like you're particular on details. I thought at first I was going to put semicolons, but then I noticed the book used commas. I forgot to get that. Okay. So, I was just going to point out to you y, the zeroth derivative of y is y0. The first derivative of y is y1. The second derivative of y2. That's what the subscripts are. You could have put anything there you wanted to. So this will be y to the n minus 1. Okay? But that is n things, because you start with 0 here. If you count how many of these you got 1, 2, 3. So the number of the ones you got is always one more than your subscript, or one more than your derivative. So this will give you n of these. So if you have an nth order derivative, you got to have n conditions. You'll need a condition for each order of your derivative, okay, to get to a particular solution. Okay. Now, that's called an nth order, okay, because the order of the derivative is the nth order. initial value problem. Initial, I'll write it this time, and you'll probably never write it again. Initial value problem. And from now on, I'm going to call them IVPs. Okay, initial value problem. That's what that stands for. Now, when I was in grad school, I was a member of an organization called InterVarsity Christian Fellowship. They had a publishing house. It was a really nice publishing house, and it was called InterVarsity Publishing, IVP. So we always talk about IVP books. So I'm always thinking, when I see an initial value problem, I think books, but it has nothing to do with it. Okay. Now, these individual things here are called your initial conditions. So these are called, from now on, ICs. Okay? These are your various initial conditions. You have to have one for every order that you've got in order to uniquely define one and only one solution. You have to have enough initial conditions, one for every order in your differential equation. Okay. Most of the time we're going to stick with 1 and 2. We're not going to be having so many of them. Okay? Now, this is the geometric interpretation, which to me is pretty lame, but it's okay. dy dx is equal to some function of x and y. That's all you got, because your first derivative is here, so that's x always there, y. So, what's the order of this differential equation?
Y is the dependent.
Yeah, what's the order? Remember?
Oh, it's just 1.
1. Order 1. So how many initial conditions do you need? 1. So all you need to know is y at some value x0 is going to be y0. That's all you need to know. Okay? So there's your initial condition, the subject to that initial condition. Okay. Now, we don't know the function. We don't know anything about the differential equation. We don't know anything about it. Let's just imagine these are various solution curves. You have an infinite number of them. Okay? Now, when x is equal to x0, y is equal to y0. So you find the curve that has that point on it. That's the curve you're going to be in. That's your solution. These others were solutions of a differential equation, but not for that initial condition. So your initial condition identifies that one particular curve, that one solution. Okay? Now, let's do it for a second order. Okay? I'm going to go to a clean page. Is that all right? Okay. d2y dx squared is equal to some nebulous arbitrary function, always of x, your independent variable, now your y, but also your y prime, because this is second order, so you go up to there. How many initial conditions do you need? 2, because it's second order. So what will they be? F of x0, or let me say y of x0. Actually, no, let's do y of x0. Don't want to confuse that. Okay, y of x0, we're just going to name y0. That's something. It's just some value, you know. It's not something that's unknown. And then the next would be?
It'd be y
prime at x0. You always do it to the same value x, okay? Whatever that is, okay? And that we usually call y1, because it's first derivative y2. Now you got 2 of them. Okay, now it's kind of hard to draw the graph of this one, though they do one. Okay, I'm sorry, they do it here. is able to do it. Okay? If you were to solve that and come up with all these family of solutions, all these curves, there's an infinite number of them, we're just showing a few of them. Well, this tells you at x0, your y0 is that value, but at x0, your first derivative, y prime, is this value. Okay? So that identifies both the point on the curve and what direction the curve has to be going there. So that identifies that curve uniquely. Okay? And of course, if you kept going up, then you'd have not just the point, also the first derivative, also the second derivative. So each of these would then identify something that enables you to know exactly which curve you're on. Okay? That's what your initial conditions do for you. Okay. All right. I'm pushing the limit of my bladder break, but I think I can do it. Okay. We're so close to the end. I think we can hold on. Unless somebody else is in dire straits. Are you? Everybody okay? All right. We'll go. All right. Let's do example 1. In problem 45, which I don't think you've done yet, in exercise 1.1, you're asked to deduce that. Let me go to a clean page here, just in case this takes more room than I'm anticipating it does. Okay? Y is equal to c e to the x is a one-parameter solution of the simple first-order differential equation y prime is equal to y. Okay? And every solution is valid on minus infinity to infinity. E's are identified everywhere. Okay? Now, that's going to give you a whole family of solutions. Every exponential function you could possibly draw is going to be a possible solution. Okay? And there's an infinite number of them. Okay? But this time we're given a initial condition that y of 0 is equal to 3. Now, again, initial condition doesn't always mean that independent variable is 0. It just means some value, we know what it is. This one just happens to be 0. Okay? And we know the y value then would be 3. So, what we do is plug in for the y, 3 is equal to c e to the 0. You plug in 0 for the x, right? Make sense? Okay? What does that tell you? What is e to the 0? 1. So that means c is equal to 3. So now you don't have a family of solutions, you have one solution. Go on and plug this back in, y is equal to 3e to the x. There is the one and only solution that's going to satisfy that differential equation with that initial condition. That's what your initial condition does for you. It enables you to solve for the c. Okay? When you solve for the c, plug that back in. Now you have the unique differential equation, not an infinite number of them, one solution to that differential equation with that initial condition. The initial condition enables you to narrow down to one and only one curve. Okay. Does that kind of make sense? I didn't think that would take much room, but just in case it did. Okay? Now, what if we demand that a solution curve, this is the B part, pass through the point 1, negative 2? Is this the same curve? I think it is. Okay? Instead of 0, 3. Okay? So now we're going to say it goes through 1, negative 2. We say it has to pass through that point. Can you say that same thing as an initial condition? What would be your initial condition? Same differential equation, same solution. Right. Oh, there's the solution. Same solution, same differential equation, same interval of whatever they call it, definition, interval of definition. What would be the initial condition corresponding to the saying it has to go through that point? Well, what would be the initial condition? Yeah, you know it. Y of, what's your x value? In that point. 1 is equal to -2. The y value is -2. So this is the initial condition that corresponds to saying it has to pass through that point. It says when x is 1, y is -2. So y of 1 is -2. Okay? So let's take the same one we had before with this as the solution and plug that in. And what do you get? -2 is equal to C times
e to the 1.
E. Yeah. So what would C be then?
C equals -2 divided by e.
That's it. That's just some number. It's an irrational number, but it's just some number. So on your calculator, put -2 divided by e to the first. There's going to be your C. It will be an irrational number. It goes on and on and on, so best we can do is approximate it. But that's exactly what the value is. Okay? All right. Now, I'm not sure the Okay, so here's then how we write our solution. Here was the general solution. Y is equal to C e to the x, right? Now, for our C, we put -2, and they're going to write it this way. Y is equal to, so let me write it the same way they do, -2 e to the -1. You agree? Okay. Okay? So we'll say -2 e to the -1 e to the x. Now, I ask you a question. If you're multiplying same base, different exponents, what do you do?
It's just going to be -2 e to the -x.
You're multiplying exponents. Same base, you add the exponents. So the easiest way to express this answer would be -2 e to the x minus 1. So there is your solution. Okay? You could write this in front, but you see this way you're eliminating the need for that irrational number. Okay? You don't have to write that C down. You can write it this way. And it's a much easier thing to deal with. Okay? So there is your solution, -2 e to the x minus 1. Okay. All right. Let's see. Yeah, I think we have time to do example 2. Ready?
Yes.
Any questions before I erase this? All right, example 2 on section 1.2. The interval of definition of a solution. Problem 6 of exercise 2.2, they'll be asked to show blah, blah, blah. We're not anywhere close to that yet. Okay? But it says show that a one-parameter family of solutions of the first order differential equation, y prime plus 2 xy squared is equal to 0. Okay? And they're going to say, you'll be asked to show that the solution for that is y is equal to 1 over x squared plus c. I'll put parentheses on it, though you don't actually have it if you have to if you write it that way. Now, if we impose on that, there's a solution. Now, do you feel the need to go back and verify, or are you just going to take its word for it? I was afraid you were going to say that. Okay. All right. So what if we impose this initial condition? Y of 0 is equal to 1. Oh, minus 1. Okay. So how would you determine what your solution is now? And what would you plug in where?
Would you plug it in for the x?
Okay, and what would you plug in?
1 plus c.
Second?
1 over 1 plus c.
Oh, 1 over, how did you get 1 plus 2? Oh, what did you say?
Plus c.
1 plus c. How did you get 1 plus c?
Well, I thought y of 0 basically is like f of x. But that would equal y.
Okay. You're trying to confuse me, aren't you? Okay. No, I'm just kidding. Recalibrate.
You plug in the negative 1 on the y.
Negative 1 for y, perfect, is equal to,
X squared plus c.
and what's your x? Oh,
0.
0, so that would be
C.
C. That's yes in Spanish, right?
Yes.
Okay, yeah, C, okay. So what does that tell you?
C is equal to -1.
Negative 1, got it. So now we go back and say your solution to this differential equation with this initial condition is y is equal to 1 over x squared minus 1. See?
C.
See, yeah, C. Okay. Now, that leads to a problem, though, doesn't it? Anyone see any problems here? The title of this is Interval I of the definition of your solution. What does this automatically do to you? Okay. The interval is also the domain of the function. What's the domain of that function?
Can equal 0. So
Huh?
can equal 0. Oh.
Oh, okay, what?
The -1 would equal 0 because of the x squared.
Okay. Say that one more
We're
time.
looking at the y equals
Right.
1 over x squared minus 1.
Right. How about let's do something to that x squared minus 1? What would be a good thing to do to it?
Put it up.
How do you mean that?
Make it a parentheses.
Okay. Like that?
Oh, yeah, you can just factor.
Oh, factor it. That's what you meant by splitting it up, huh? Okay. What does that be?
X plus 1, x minus 1.
No. Yeah, I'm sorry. X. I'm sorry. I don't know where I got the y from. Okay. X minus 1. X plus 1 times x minus 1. Okay. Now, go back to what would be your interval of definition. Guess what it can't include? Or -1. So your interval of definition either is going to be minus infinity to minus 1, or minus 1 to 1, or 1 to infinity. It can't be all three. It has to be one of those three. Okay? Now, we need to know which one it needs to be. Well, it's pretty obvious because this was your initial condition, 1, 0, y of 0 is equal to 1, right here. These are out of the picture. These cannot be considered because your initial condition is right here. Y is equal to 0. X equals 0, so you have to be in that. So this is not a possibility. That's not a possibility. You're limited. Your interval of definition has to be minus 1 to 1. Now, with a different initial condition, you might be in one of the other two, but you're never going to be in more than one interval. Okay? Make sense? The initial condition, yes, it told you what your constant had to be, okay? But it also told you what interval you have to be in. So that was a sort of a hidden feature that you probably didn't realize you got with that. Okay? All right. If you just considered that answer as a function, then you could be in any one of those intervals. But because this is part of a differential equation with an initial condition, you are limited to that one. Okay. All right. Let's move on to example 3. They grind it to death here. I think we've hit it all. So let's move on to example 3 now. Not certain we're going to have time to finish example 3, but let's give it a shot. Back in your back in the example in 1.1, example 9 and 1.1, we saw that here was a solution. X is equal to C1 cosine 4t. We did that a little earlier today. Plus C2 sine 4t. Okay? We had them separately and then said, or you could add them together. It's a two-parameter solution of this differential equation, x double prime plus 16x is equal to 0. Okay. Now, it says find a solution of the initial value problem. So here's your initial value problem. Same differential equation, x double prime plus 16x is equal to 0. How many conditions do we need? 2. Okay, the first will be your x evaluate some value of t. This value is going to be pi halves. Okay, and they tell us this is going to be -2. They also tell us the x prime at pi halves is equal to 1. Now, time out for a moment here. Notice that for initial value problems, the x value has to be, this problem is the t value. The t value has to be the same for both the function and its derivative. That's why it's an initial condition. If they were different, then those are called boundary conditions. We'll get to that a little bit later, okay? Boundary conditions are not as specific as initial conditions. For initial conditions, you need to use the same value for your independent variable, but you have to have all of your x's and x primes, the same number of those as you have degree of the differential equation. Okay, so now we've got 2. So what do you reckon we're going to do? plug it in. But what are we going to plug in? Tell me that first.
Pi halves into t.
Where?
T.
Yeah, but in where?
Cosine 4t.
Okay. You plug this in here.
Yeah.
Okay. So this will be x is equal to C1 cosine. Now 4 times pi halves would be what?
That'd just be 0, right? Or no.
4 times 2 pi, 4 times pi halves. What is 4 times pi halves?
Oh.
4.
No. That's 2 pi.
Okay, that is going to be 2 pi. Okay? And you know that has to equal to minus 2. Right? Well, what is cosine of 2 pi? 1. So therefore, C1 has to... Oh, wait. You got me going in circles here. Wait just a second here. You have to plug it into the whole function. Okay? X equals C1 cosine 2 pi plus C2 sine of 4 times pi halves is 2 pi still. Okay, that's good. And what sine of 2 pi?
0.
0. Okay. So we have now C1, let's see. And we know this is equal to negative 2. Okay? All right. Well, if this is 0, then that whole thing goes to 0, and what we have here is C1 is equal to negative 2. There we've got what C1 is. Okay? Now what do we do next?
Plug in negative 2 for C1.
Plug in what?
Plug in negative 2 for C1.
Okay. Yeah, okay. I'll buy that then. So you're saying x is equal to negative 2 cosine 4t plus C2 sine 4t. Is that what you meant? Yes, that's a good legal thing to do. But what else do you do?
Plug that. Oh, take a derivative?
Ah, you got to take a derivative. X prime is equal to,
so that's gonna, you gotta bring out that 8, you gotta bring out that 4, so it'd be negative 8, then it'll be a positive because you're doing the sine. So sine of 4t. Minus 4.
wait, where do you get minus?
Oh, no, not minus, sorry. Plus 4 cosine 4t.
You got your C2,
C2.
cosine 4t. Right? Okay. Now let's plug in for t pi halves. So you have x prime is equal to
We put in pi halves.
plug in pi halves for t, right?
Okay. So it's just 8. Will that just be 0?
Okay, so this will be 0 plus 4
C2.
C2
And that just be 1.
1. Okay, so 4C2, and that has to equal 1. So what does that tell us?
C2 equals 1 over 4.
Yeah, C2 equal 1/4. So we go back to our original equation. Here's your solution. For this initial condition, that differential equation, in this initial condition, it is x is equal to 2 minus 2, sorry. I looked at the wrong line here. Your C1 was minus 2. So minus 2 cosine 4t plus 1/4 sine 4t. that differential equation will go through this point, pi halves minus 2, and we'll have a slope at pi halves positive 1. So that is the one particular solution for that initial condition. Those initial conditions. You have two of them because it's a second degree second degree differential equation. Second order differential equation. Right? All right, good deal. Let's see if they got it right. X equal minus 2 cosine 4t plus 1/4 sine 4t. Yes. And they say a solution, it is the solution. There you can leave off the a's now and do the these. And I do believe we may have run out of time, did we? Sorry about that. All right, so we'll pick up next time with existence and uniqueness. Okay? Let me erase this mark down here.
So the answer is x equals -2 cosine?
That's it right there, yeah. Okay. Right there. -2 cosine 4t plus 1/4 sine 4t. Good deal. So we'll pick up next time there. Homework exercises in 1.2, I think you can do number 1, especially if that's in the back. Do either 3 or 5 if they're in the back. Think you can do either 5 or 7 or 9 if they're in the back. And I think you can do 11 or 13 if they're in the back. All right, I think that's probably enough for there. We'll probably do a few more later when we finish the section. Don't have many more to go here. Any questions? Good deal. All right. Okay, got it. All right. Now, you better check with registrar's office and make sure things are right. Yeah.
Just a warning. Once I fix that, I'm gonna have a problem with schedule. I might be on. Okay, once I get that done and get in your class,
right.
I'm only gonna be able to come Thursdays.
Okay.
Since I have another class that starts like after this, but it's on the Birmingham campus.
Right.
So I won't be able to take both at the same time since I don't have a ride. So
okay.
I might be only able to come.
Well, you know I record every class.
Yeah, that's
okay.
That's what I'm asking. It's like, okay.
That's fine with me if you're okay with it. Yeah. Okay? All right. All right. So let me shut this down.